When light waves pass through a small aperture, an interference pattern is observed rather than a sharp spot of light. This behavior indicates that light, once it has passed through the aperture, spread beyond the narrow path defined by the aperture into regions that would be in shadow if light traveled in straight line. Other waves, such as sound waves and water waves, also have this property of spreading when passing through apertures or by sharp edges. This phenomenon, known as diffraction, can be described only when waves modeled for light. So far we have learned that an interference pattern is observed on viewing screen when two slits are illuminated by a single wavelength light source. If the light traveled only in its original direction after passing through the slits, the waves would not overlap and no interference pattern would be seen. Instead, Huygens' principle required that the waves spread out from the slits. In other words, the light deviates from a straight line path and enters the region that would otherwise be shadowed. This divergence of light from its initial line of travel is called diffraction. In general, diffraction occurs when waves pass through small openings around obstacles or past sharp edges. When an opaque object is placed between a point source of light and a screen, no sharp boundary exists on the screen between the shadowed region and an illuminated region. The illuminated region above the shadow of the object contains alternating light and dark fringes. Such a display is called diffraction pattern. A single slit placed between a distant light source and a screen produces a diffraction pattern. It will have a broad, intense central band. The central band will be flanked by a series of narrower, less intense secondary bands called secondary maxima. The central band will also be flanked by a series of dark bands called minima. The result of the single slit cannot be explained by geometrical optics. Geometrical optics would say that light ray traveling in straight line would cast a sharp image of the slit on the screen. If the source of light and screen are at a finite distance from the obstacle, then the diffraction called Fresnel diffraction. And if the source of light and screen are at infinite distance from the obstacle, then the diffraction is called Fraunhofer diffraction. In this discussion, our attention will be on Fraunhofer diffraction, which occurs, for example, when all the rays passing through a narrow slit are approximately parallel to one another. This can be achieved experimentally either by placing the screen far from the opening used to create the diffraction or by using a converging lens to focus the rays once they pass through the opening. A bright fringe is observed along the axis at zero angle, with alternating dark and bright fringes occurring on the either side of the central bright one. Figure is the photograph of single slit Fraunhofer diffraction pattern. We can deduce some important features of this phenomenon by examining wave coming from various portions of the slits as shown in the figure. According to Huygens' principle, each portion of the slit acts as a source of light wave. Hence, light from one portion of the slit can interfere with light from another portion, and the resulting light intensity on viewing screen depends on the direction theta. To analyze the diffraction pattern, it is convenient to divide the slit into two halves, as shown in figure. Keeping in mind that all the waves are in phase as they leave the slit. Consider ray 1 and 3, as these two rays travel toward viewing screen far to the right of the figure. Ray 1 travels farther than ray 3 by an amount equal to the path difference A by 2 sine theta, where A is the width of the slit. Similarly, path difference between ray 2 and 4 is also A by 2 sine theta. If the path difference is exactly half a wavelength, corresponding to a phase difference of 180 degrees, then the two waves cancel each other and destructive interference results. This is true for any two rays that originate at points separated by half the slit width. Because the phase difference between two such points is 180, therefore, waves from the upper half of the slit interferes destructively with waves from the lower half when a by 2 sine theta equal to lambda by 2, or when sine theta equal to lambda by a. If we divide the slit into 4 equal parts and use similar reasoning, we find that the viewing screen is also dark when sine theta equal to 2 lambda by a. Likewise, we divide the slit into 6 equal parts and show that darkness occurs when the screen bends sine theta equal to 3 lambda by a. Therefore, the general condition for destructive interference is sine theta equal to m lambda by a. Sine theta equal to m lambda by a gives the values of theta for which the diffraction pattern has zero light intensity, that is, when a dark fringe is formed. However, it tells us nothing about the variation in light intensity along the screen. The general feature of the intensity distribution are shown in the figure. A broad central bright fringe is observed. This fringe is flanked by much weaker bright fringes alternating with dark fringes. The various dark fringes occur at the value of theta that satisfy equation, which is sine theta equal to m lambda by a. Each bright fringe peak lies approximately halfway between the bordering dark fringe minima, and the central bright maxima is twice as wide as the secondary maxima.